Hello folks. In this module we're going to talk about the standard deviation and the variance of a sample. Just a quick review of what we did in class. I have already taken a very small sample of scores. These are supposed to be times. For example, how much time it took for each subject in an experiment to solve a problem, let's say, in seconds. So we've got only 5 of them. I've figured the mean already by taking the sum of all those x's, which is 150, dividing by n, 5, to give us a mean of 30. What we want to know now is how do the scores distribute themselves around the mean. And the really logical thing to do, I think, therefore, is to take the deviation of each score from the mean. So this column represents a simple subtraction. Every x score minus that mean of 30, which gives us some negative signs and some positive signs. You may recall that the definition of the mean is the point in a distribution that is perfectly balanced by the scores above it and the scores below it, so that the sum of all those deviations, both positive and negative, must always come out to be 0. The mean is sensitive to every one of those deviations. Now what we want to know, though, is something about how much variability there is around that mean. The deviation scores make sense to look at, but as we've seen, the sum of them is 0, so we're not going to just take a simple average. In fact, it turns out that the method we're going to use has some very nice qualities to it that we'll see a little bit later. We're simply going to square each one of those deviations. So if we take -6 squared, we get 36, and as you can see, this is going to get rid of all those negative signs. And to sum up all of those squared deviation scores, I've done this in advance, we get 314. 314 is a number called the sum of squares. In fact, we're almost there. We are almost to the point of having the variance, and then there's just one more step to getting the standard deviation. Let me show you what we've done so far by giving you a formula that summarizes this. We have simply summed up all of the squared deviations around the mean and come up with 314. If that's the sum, it would be very simple to simply take an average of that, and in fact, that is what the variance is. Sample variance, designated by lowercase s squared, is nothing but the sum of squares divided by n. So in this case, 314 divided by 5, which gives us 62.8. Well, that is nice enough. The bigger that number comes out to be, basically it means the more spread there is around the mean, but it is in squared units. We started in seconds in this example. This would be seconds squared. It might be nice to be able to express it back in the original units, and that's exactly what the standard deviation does. The standard deviation is nothing but the square root of the variance. Sum of squares divided by n, but we take the square root. So in this example, square root of 62.8, and that comes out to be 7.92. By itself, the numbers 62.8 for the variance or 7.92 for the standard deviation don't tell you an awful lot, but by comparison, if you had maybe 1 or 2 other conditions, you could see if the standard deviations were different. And basically, the lower that number, the less spread there would be in that data set. Now, a fairly simple concept once you've done it a couple of times. However, this way of computing the sum of squares, even though it is, I think, logical because it conforms to essentially the definition of the sum of squares, it's not the easiest way to do the calculation usually. So I'm going to show you that we can get the sum of squares in another way called the raw score formula. This is often called the deviation score formula. The raw score formula doesn't require that we do any of the subtractions to get those deviations, and then doesn't require that we square them in any way. We simply deal with the raw scores that we start with. And it looks like this. Now, I'll bet initially this doesn't look to you as if it's an easier formula, but it is. We often get to bypass any decimals to get magnified when we square them in using this formula. So let's see what we get when we actually follow this. This first term tells us to square each of the raw values we started with and sum them all up. So we're going to need a column that has all of those numbers squared. Now, I'll admit those are fairly large numbers. Here's what we get when we multiply those out. 576, 1600, 324, 35 squared is 1225, and 33 squared is 1089. Calculators won't give you any trouble in adding these up though, so the fact that they're large isn't that big a deal. We come up with 4814 for that term. Sum of all the raw scores squared, 4814. Next step is to take the sum of all the raw scores and take that quantity and square it. Well, we already have that. 150 squared divided by n, which is 5. So 4814 minus, well, if we square 150, we get 22,500. 22,500. Doing the division gives us 4,500. And then just simply doing that subtraction leaves us with, thankfully, 314. It does come out the same, or at least within rounding error of what you get using the other formula. In fact, if they're not exact, and it looks as if there's a little bit of rounding error, it's almost certainly going to be in a deviation score formula where you've got the little bit of error. The raw score formula typically gives you a more exact result. So, just to review, in order to get the variance and then the standard deviation, you first compute the sum of squares. That is the sum of all the squared deviations from the mean. Once you have that sum, either by this method or by this method, but this one is usually preferred. Once you have that, well, I've erased the formulas, but once you have that, you simply take the average. That is, divide by n in order to get the variance, and then you take the square root in order to get the standard deviation.